Hey guys, today we'll be looking at something called as buffer overflow. So one of the oldest trick, in the reverse engineering or the reverse analysis, something which the hackers use even today. So let's have a look at a very simple function, right? You have a C program on the left hand side. This is how the stack behaves when this program is run. So you have the main function. The first instruction to be executed is this one. So you have the parameters 2 and 1 which are like pushed to the stack. So you have 2 being pushed first, and then you have 1, and then you have the return address, right? So you need to have the return address of the next instruction to be executed, right? Because the compiler should know which instruction to be executed. That's why we actually get the address of this instruction and we dump it over here. So we push it to stack. After that, we go and create a copy of the base pointer. Now I will not go in detail about base pointers since they are not very relevant to our discussion, but I would encourage you to read about all the various registers which are used regularly, right? So once the control is given to the function, we have two variables here, C and D, which are pushed onto the stack in this fashion. So this is how the stack would look once this program is executed, right? Now what's buffer overflow, right? So that's what we are interested in. Imagine a scenario where the user has control over the parameters like C or D, and he decides to pump in huge amount of data as part of these variables. So the data which he has pumped in will basically occupy this space. It will occupy the space for C, it will occupy this region as well, and let's say it also occupies the return address, right? Once you overwrite the return address with some junk value, the machine will not know where to return to, right? So the program will crash, as simple as that. So that's the funda behind stack overflow. Well, being a reverse engineer or a hacker, I would not be very interested in crashing a program. I would be very interested in grabbing the access of the entire program. So what would I do, right? Now in that case, I I could go one step ahead, and instead of just dumping junk value over here, I could redirect, or I could basically change the return address mentioned over here to an address somewhere else in the memory where I have some malicious code or some shell code present. As you know that using a shell code, I can basically get access to the entire shell. I can basically create a shell. I would have uh, achieved a lot, and that's more than enough to create havoc in the entire system, right? So that's the funda. What we are going to do in the coming exercises, we are basically going to pump in huge amount of data so that we basically fill all of this location, right? And then in the return address, we are basically going to modify this content of this memory to address what we desire, and that address will basically be pointing to a shellcode, something which I have picked up from the Shellstorm website over here. And when this shellcode is executed, we basically get the access to the entire system. Yeah, for this quick demo, I'm using a Ubuntu machine, which is 1404 LTS, a 32-bit operating system, right? Yeah. So let's look at vulnerable code. So I have a C program here. It's a CPP program. It's a very simple program wherein the user has to provide input, as part of the command line, and whatever the input is provided will basically be blindly dumped onto the buffer, as part of the string copy function. The string copy basically copies the input which is provided by the user, into the array buff, and the array basically has just 100 bytes of memory, right? So if I can dump a huge amount of data as part of the command line arguments, I can basically overflow the buffer. So that's the whole funda which we are going to exploit here, right? Yes, so let's open up the terminal. So we are in the folder now. To start with, we will be basically disabling couple of um, counter measures which have been introduced to prevent buffer overflow, right? There are a lot of tricks to even bypass these features, but for now we will just go and disable them. So one of them is the address randomization. ASLR is something which we will disable using this command. Okay, maybe I'll try that again. Yeah, so we have done that. The next, we are going to use the G++ compiler to run the CPP program which we have, right? And what we are going to do is, as part of this command, we are basically again disabling the stack protector, and we are making the stack executable using this command, right? So now we should have a executable one created in the folder. Let's give a couple of permissions which are required here. Let's give the root, and let's also give the 7755. Yeah, so I think that's good. Now as I told you earlier, to perform buffer overflow, we will be providing the program with a lot of command line arguments, so that um, which will be obviously it's going to be a huge set of arguments, probably like 100 characters or more than 100 characters, since you saw the buffer what we have defined here is 100 characters, right? So we need to give obviously a character set, a string which is greater than 100 bytes. Now it would be very mundane to write 100 characters, so we could use a bit of programming over here, right? So let me show you a quick trick. So using Python, I can simply churn out 100 hellos, right? So using a simple command, I could write 100 hellos onto the screen. So we are going to use this technique throughout the rest of the demo, right? So now we know that the program, in the program we have 100 bytes allocated for this array, but we still want to understand the exact size of this buffer. It might not be exactly 100, though we have defined it, right? What we are going to do is we are going to play with it. We are going to test it, right? So let's say we run the program, and we are going to use the trick which I showed you earlier. We are going to use Python, and then let's use the print. Yeah, so let's probably print 100 of A's. I mean, let's use 100 A's as the input to the buffer overflow program which we have written, right? I think I did a small mistake over there. Let me just correct it. So yeah, there is a mistake over here. Let me quickly correct it. Yeah, so you see the program executed successfully, which means the buffer accepted the 100 bytes of A, 100 A's which we provided to the input, right? Now let's change this to, let's say, 110. Let's see what happens then. Yep, even 110 works, right? Now let's increase it to 112. Yeah, so we got a segmentation fault, which means the the stack, the size of the stack is 112 bytes, right? So that's why we got a segmentation fault over here. So now that we know the size of the stack, what can we do? So on the screen you see this is what we are seeing. We have like 112 bytes of the stack available to us. So we are going to fill this stack with 112 bytes. Now as I told you earlier, in order to get access to the shell, in order to get control of this entire system, we need to run the shell code, right? So we as part of this 112 bytes, we are going to put few bytes which will correspond to shell code. The shell code which I have obtained from Shellstorm website is around 45 bytes. So we are going to have 45 bytes of the shell code, which means we are left with another 67 bytes, which is 112 minus 45, which is 67 bytes. Now these 67 bytes I'm gonna use something called as NOPs, right? No operation NOPslets. You call them as NOPslets. I'll tell you why do we use NOPslets, right? So as you see in the screen, what we are trying to do, we have understood that the stack is 112 bytes, right? So we are gonna pump in huge amount of we are gonna pump in exactly 112 bytes, such that the next the the next 4 bytes of data will basically be the return address, and we are basically trying to overwrite the return address. So here in this case we'll be overwriting the return address to the start of the buffer, so that at one point of time we will be able to execute the shell code and get access to the entire shell. Now as I told you earlier, there are a lot of mechanisms which have been employed to prevent this kind of reverse analysis or reverse engineering. As a result, though we might run this program on a debugger and we might try to find the exact start of this particular buffer, we might still not be able to predict the exact address, because it might not be the same environment as a debugger when you actually run it on the compiler. So the return address what you predict in the debugger might not exactly match the one which you get while running the program using the G++, right? So that's the reason we have a lot of NOPslets over here. So we are going to fill the entire of the stack at the top with NOPslets, right? So let's say our prediction fell short by 2 or 3 bytes, right? Let's say our prediction was not exactly spot on. It was supposed to be this. We were supposed to predict the start of the stack, but instead we had few offsets, and we, let's say, predicted 5 bytes below, right? So let's say we predicted this, but because we have NOPslets at the start, it doesn't matter. All of the NOPslets are basically hex codes. They correspond to x90, and whenever the compiler sees a NOPslet, it basically jumps to the next instruction, and all these 67 NOPslets will be run down without executing any operation. And when it comes to shell code, what happens. We basically get access to the entire shell, right? So that's what we are trying to do. Let me go back, right? Let me now open up the GDB, the debugger, right? Yes, so we have the debugger here. So in the debugger, let's set the arguments. You need to have certain arguments which will be used while running this program in the debugger. So let's use the NOPslets which we discussed just now. So we learned that we are going to use around 67 NOPslets. So that's going to be 67. Okay, let's use exactly 67 of them. Yes, so we have the argument set. Right now let's put the breakpoint as well. Right now let's run the program. Let's run the vulnerable program. Yes, so we have reached the breakpoint, which is um, at the main, and we have the string copy function to be executed next. So let me run down to the next instruction using the command ni. Yes, so we executed the string copy as well, right? So what we have done is we have provided 67 nope sleds as the command line argument for this particular program, right? And why we are doing this, we are actually trying to find the start of the buffer, over here. I mean, we might not be able to find the exact start, but we are trying to find the address of the memory location which is very close to the start of the stack, right? So now let's look at the memory locations, right? Let's look at the 200 memory locations in the stack. So I'm using this command which will help me obtain that. Okay, so what we are looking here is we have pumped in around 67 nope sleds, and as I told you, the nope sleds are nothing but x90 codes. So just look out for x90, right? Yeah, so I can see some x90s over here. Maybe it would be better if I can increase the size probably to 250. Yes, so probably, yeah. Yeah, so you see over here we have the nope sleds which we had earlier provided to the debugger. These are the 67 nope sleds which we had given, and they are basically sitting in this part of the stack, right? So you see the nope sleds will basically start from this location, that's BF FF F3 40, and it's not exactly 40 because you have like 4 bytes over here, and then you have another 4 bytes, so we have probably the nope sleds starting from 48, right? So let's probably note this particular location. Let's note this down, right? Probably let's note it down over here, right? Let's note it down as 48 because that's what we saw, right? It's not exactly 40. It's the first 8 bytes are already taken by some other values, so we have the nope sled starting from 48 onwards, right? So yeah, we have taken down the memory location over here, which is fine. Now what we do is yeah, I think that's the only thing which we had to do here, so we can exit the GDB from here, right? Yeah, let's go back. Yeah, so what we are going to do now is we have to we have obtained the starting address of the buffer, right? We have obtained that, and that's nothing but this one, yeah. So we know the starting address of the buffer. So let's go back to this diagram. So because we know the starting address of the buffer, what we are going to do is we are going to go back to the code, and we are going to just run it with 67 nope sleds and then 45 bytes of shellcode and the return address, which will be this one, right? So we are basically going to tamper with the actual return address. We are going to modify this return address with this one. We are going to replace that with this one, so that when the program executes, it basically jumps to the start of the stack, and we are able to run whatever is present in the shellcode, right? So that's what we are trying to do. Yeah, so what we'll do is how do you run a program? We run it using vue-ln, and then let's use Python, right, to generate the huge amount of data which we want, right? So that's this one, and the next is we will be putting in our 67 nopslets, right? So that is done. So we have 67 nopslets at the start, and then I will basically copy the shell code, the 45 bytes of shell code which I showed you earlier, right? So that will be copied. So let me copy that. Yes, the shell code is also written. Now the next thing what we'll do is we are going to place the return address, right? We are going to place the return address which we obtained. We have it as 48 over here, but as I told you, due to the presence of nopslets at the start, it need not be exactly 48. So let's use 50, right? Now the tricky thing here is because we use the little Indian, right, kind of architecture, right? So what we'll do is we'll have to put in the least significant byte first. So instead of using 48, let's use 50. That should work, right? So let's do that. Yeah, so we have written the return address as well. So this is nothing but we have just reversed the address over here because of the little Indian architecture. So we have 50 and then XF, we have F3, FF, and then BF. It's the same address, but it's written in a reverse manner, right? So I think we have the required set of inputs over here to cause a buffer overflow and gain access to the system, right? So let's run this. Yeah, so let me run it once again. Yes, so I think we have obtained the control of the entire system. You can run a command like whoami, and you should be you should see root displayed over here, which means you have actually got the control of the entire system, right? So you were able to exploit the buffer overflow vulnerability and you got into the entire system. So that was a very simple demo for buffer overflow exploit. Hope you guys liked it. Thanks.